Thank you to everybody at UE for having us back this year. It's always a good relationship. In this presentation, I hope that it is very involving in what we call across the bridge technology. We manufacture electric motor test equipment, and generally that's where we focus. But we were constantly asked about, well, can you give us an indication of this, or can you help us out here? That becomes very critical if we're inside of a nuclear power plant. And these main feed pumps or the main coolant pumps, they can't get vibration equipment on them, right? It's not easy to, most people don't volunteer to go in containment, unless, I heard they pay pretty good, but I wouldn't volunteer for that, right? So there are certainly some telling signs within the electrical side of the industry that can be an indicator, a premise per se, maybe, and we call it crossing that bridge, right? Where the ultrasonics and the vibration, you guys are involved in a lot of different things. You can look at pumps, bearings, you can look at valves, everything under the sun. We don't really play in the mechanical world that much. However, things happen in the mechanical world that create indications in the electrical world. And so I wanted to try to marry them up a little bit today and give you guys a little indication of what you might be able to use to correlate with the efforts you're putting forth in ultrasonics. Okay? So, process analysis, your path to system knowledge, right? It's going to be an interesting. We start with the hidden sensors. Okay? Now, what do I mean by a hidden sensor? I'm standing here today telling you that you have literally hundreds, and some of you maybe thousands of sensors installed into your facility right now, and you're not aware of it. Okay, as an example, you may have, we've all seen this looks like a pump maybe, of the centrifugal type. And if someone thinks it's something different, speak up, it might be. Okay, this is the first time I've gotten to give this presentation, by the way. I'm very excited about that. And so what's hidden in here? There's a variety of things. It looks like it's set up for sensors, doesn't it? Maybe 4, okay, but those aren't the ones I'm talking about. Those are the ones you already know about. Those might be points where you're taking ultrasonic measurements, or you're actually taking vibration measurements, right? But there's another sensor in there that you're not aware of. What about this one? A fan. It's a little bit off balance because it's only got one blade, but the same thing matters, right? It's a fan, and we got a lot of variety of places you guys might actually try to take ultrasonic tests on, okay? Get readings from to try to measure bearings or something to see if there's something going wrong. But there's another hidden sensor in there that we're just not aware of yet. Has anyone cheated and gone ahead and read and know the answer to the one? No, not you guys. You're not allowed. Another one, okay? This looks like a compressor maybe? Blower? Blower, okay, very good. Again, 4 spots for things, but there's something hidden in there as well. And finally, one more. It looks like a conveyor belt, gearbox, with a variety of test points, right? So the question is, out of all these, what is common? Right, Pierre, you got it, it's a motor. Of course, you can imagine we make electric motor test equipment, so that was fairly deductible. So you've gone through all the work to install all these motors, and they're designed to run an application, right? Okay, so the question is, how can we be looking at those as sensors? Well, this was an interesting little picture because it was a tearaway. And if you ever visit our facility, we got a lot of these sitting around to kind of give more of a training aid. Hey, what does the inside of a motor look like? There's a lot of things that go roundy, and they're hidden. It's just not this piece of steel that goes, there's a lot of things involved in it, right? Well, one thing it is that most people don't take advantage of, or they don't really relate it to that level, is that is a sensor in itself, okay? It's like a transducer. A lot of you guys have walked around with a multimeter or something, and you actually placed a probe onto something and said, hey, I'm going to use this probe as a transducer, okay? Well, why couldn't a motor be the same thing? And that's really what we're here to focus on today is, hey, they're out there, they're connected to your applications, how can you use them to your benefit, okay? So with that, we're going to take this, we're going to talk about the electrical to mechanical, back to electrical, okay, transition. And this is pretty straightforward. You've all been involved in it at some point. Switch sides here so I'm balanced. But this is a little animation to kind of give an idea about this. But this is basically for every mechanical event that occurs in your process, all right, you can expect there to be some electrical indication of that. Okay, now how strong it is, how well it shows up, again, all that has yet to be determined based on your process, okay? One of the things that, we try to do in our testing is actually try to identify the speed of a motor. That for the most part, we identify the speed of a motor based on the slightest imbalance of a motor, okay? And the more imbalanced a motor is, the easier it is to tell the speed. This is not so untrue in vibration as well, but it's usually a little bit easier, okay? So So again, anything mechanical creates an impact. Now, if you think about a motor, all right, we have the rotor, it turns, all right, and the rotor turning through the gearbox creates movement on that conveyor belt, right? So that's mechanical energy. I've taken electrical and I've turned it into mechanical, right? Makes sense. And it went awful fast, but we apply three-phase to the stator windings. It induces power onto the rotor turning through the gearbox makes that conveyor belt turn. Well, let's say something goes bump in the night. That bump in the night is going to be transferred back to the rotor, back to the stator, and back up into the power system, which is detectable by an electrical device. That just happens to be ours. It could be anybody's. It just happens to be ours. Now we've gone from electrical to mechanical and back to electrical. Okay, and we're using the motor as effectively a transducer for this. Okay? Now, every one of your motors in your plant is hooked to some type of application, is sitting there waiting to be taken advantage of. Okay? And whether you're testing electrical, whether you're testing vibration, ultrasonics, a lot of times you're going to go to the motor and you can actually see a lot of things happening, okay, on the electrical side, okay, on the mechanical side in electrical. So just a little bit of animation to kind of give you a taste of what is available out there, okay? So hidden sensor is the goal. If you're talking about a hidden sensor, that's what we're referring to, okay? So how many, question?
Yeah, what would you be tracing on the scope there?
And that, by the way, I drew that personally, so it's a pretty ugly spectrum, okay? But let's say that, and I've only showed one flash of an event that occurred, okay? But let's say that from a conveyor belt perspective, let's say that it was being loaded on an odd way, or one of the bearings from within the conveyor belt was starting to drag and create a torsional load, and that's really what we're after. It takes a torque variation for us to see it. Now, a lot of people say, well, why don't you guys see bearings? I'm not going to talk a lot about bearings because although we have had some success in identifying bearing frequencies from the spectrum, our research, as well as much of the academic research out there, and I'm talking, when I say academia, I'm talking about colleges, universities, all this kind of stuff, says that the bearing failures need to be late stage 2, early stage 3 before current and torque start being greatly affected. Now, you'll hear different opinions from different people, right? And I'll respect their opinion on that, okay? Some of our competitors, per se, will say, oh no, current's going to be the next big thing in bearing analysis, and we're just not there yet. Okay, between ultrasonics seeing it at the natural bearing frequencies and vibration at the defect frequencies, we're much later in the game. Okay, now if you've got a motor hidden deep inside a reactor system that you can't get to, well, you'd like to know you got a stage 3 bearing failure coming, right? You might want to start to shut that plant down a little bit. It's coming. We can tell when it's there. Okay, but by the time stage 3 is there, you could hear it if you were standing next to it, right? So we are not going to be all is to be on bearing analysis, okay? But if a bearing failure was creating a torsional load change on a conveyor belt, if the way the material was being dropped on the conveyor belt has changed from previous readings, now you can see it's going to show up in current, okay? So again, we're just trying to cross that bridge halfway. Here's what a lot of times happens. We had a case study recently where the current signature data, okay, was indicating a significant increase in what we would blame on an imbalance, okay? We can't differentiate so much between balance or alignment. We just know that it was a mechanically induced, generated, broadband energy. So they contacted who? The vibration, the mechanical analysis group, right? Which would be a lot of you guys here, right? And they said, hey, something's strange going on with this fan. Okay, this was a belt-driven fan. So they go out and say, yeah, you know what, it was misaligned. But they had just aligned it, so why were we seeing that? Well, they had aligned it cold. Okay, so when they went back to check it again, hot alignment changed it quite a bit. So they were able to get that done. Well, we went back out, I think, 3 months later, and a lot of generated frequencies were back. So we verified, we kind of followed up, said, hey, everything's gone, but it came back. Well, it ended up that alignment issue had created it started to fail one of the bearings. Okay, I guess the tension on that bearing had been sufficient that it had created a failure mechanism. So we were identifying it again. Now, the very next vibration route would have saw it as well. We just happened to be out there, we tested, we say, hey, it's back. And they went out and said, oh, now the bearing needs replaced. Okay, so this is the correlation, again, where we're going to be very much qualitative. Okay, you guys can be more quantitative. Right? So if we're saying, hey, look out, there's something happening, I kind of like it as a burglar alarm. We're a mechanical burglar alarm. Okay? And then we like to turn it over to the guys who actually have quantitative mechanical analysis. Okay? If you got your ultrasonic gun on it, you're giving a quantitative value to what we're seeing qualitative. We say, hey, look, there's something wrong. Not sure exactly what it is, kind of like your house burglar alarm. Burglar alarm goes off, you're not sure. Is a kid sneaking out? Is a dog going to the door blow open? What happened? Until you get up and start looking, you don't know, right? Unless you're got a much more advanced alarm system than I got, okay? So and maybe you do. But anyway, so that's kind of where, good question. I'm glad you asked that, and thank you for asking that. So that's kind of what we're looking at in this screen here. Speaking of qualitative and quantitative, let's go into that just a little bit and make sure we understand the differences in what's available. In this situation, this would be more quantitative. Okay, quantitative being an absolute value that you can make a decision on based almost on like a standard. Okay, and those are great to have, but not always are they the first indication, right? These are a lot of times where you have to be trained on and compare it to. So in this situation, we're seeing what we call an inrush startup. Okay, it's a current that's captured through the inrush, and if you've ever heard me talk about our technology, I love that inrush startup. Right at the beginning of life, and we talked about Pierre during the break, that inrush startup is everything, because you can base a lot of changes on this. Okay, if 6 months you're going through the same startup, guess what? It should be exactly the same. Okay, the only thing that's going to change, even with a load change, is this part right here. Okay, the initials shouldn't change. Okay, but the amplitude of this should not change, but the length may change based on if you have a load variation. Okay, it's Ohm's law at its finest, in my opinion. Okay, and a great trending and troubleshooting tool. Analysis of amplitudes and values. Okay, so for quantitative, I want to know exactly what that value is. Okay, the motor manufacturers basically say, hey, we expect a certain amount of inrush, and if you're not getting that, it's a problem. Okay, so that it's a key element. Industry standards are usually supporting us on that. Okay, now some of the motors are changing these days, so if you're able to get a current reading on some of these motors, recognize that some of them are being designed to exceed 10 times, okay, their full load amps for inrush. Okay, and it shouldn't surprise you, but here's the thing, it won't surprise you if you get that baseline, right? That's such a good baseline. All right, so yeah, should definitely be getting that. All right, so in terms of we can actually exactly what is the start amplitude and exactly what is the startup time, both independently. A quantitative comparison. It was 5 seconds. Well, actually, in this situation, it was 3.2 seconds. Last time, why would it be any different this time? Okay, as long as you're running the same process and the same load, okay, it should be exactly the same. All right. So inrush is based on the stator health and pretty much just Ohm's law. Startup is based on the torque delivered and the load that is being seen. Okay, some very simple thought processes, but that's quantitative. Another quantitative, okay, right here, this is for I don't remember what this actually was. I'm pretty sure it was a pump, but there was vanes, so it has to be, right? It's either a pump or a fan, I guess, but it's probably a pump in this situation. But there are two specific frequencies. We got the motor speed and we got the vane pass frequency. Again, a mechanical peak that shows up on your current, all right? Now, if you're thinking about a pump vane, it's a pretty simple calculation. It's the pole pass frequency, which you guys have seen the pole pass. That's the stator winding, rotating magnetic flux, and the rotor, which is slower, right? I can do that on one foot. I always like to show that on one foot. But so as these two invisible magnetic fields are turning, all right, they pass each other. And every time they pass each other, they create a flux. That's pole pass. Well, pole pass times the number of vanes is vane pass frequency, and that can be trended. Now, what could go wrong with your vane pass for you vibration experts? What does it indicate if it starts to go to rise in elevation? Balance problem, maybe a damaged vane, okay? Some type of impingement that may be occurring. So all mechanical related stuff, again, we're going to give a number, and it can be trended, all right? And as an example, here's another one just like it. Now this is 6B, here's 6A, and we've gone from 0.027 to 0.046, almost twice. It'll be a quantitative comparison, okay? So it's elevated, what's the right move? If you're the electrical team sees this, they're probably gonna call a mechanical team, ain't they? Say, hey, we've got vane pass frequencies creeping up. Is it a belt-driven pump? What could it be that's creating this elevated values? Someone should go out and try to quantitatively provide some mechanical information for that as well. So that's a little taste of quantitative. A qualitative, again, what does it look like? Not the best image, I apologize for that, we should pick a different color. But in this situation, it's characteristics and shape. It's something I'm looking at that I can say, hey, which one of these is not like the other, right? The old Sesame Street theme. But it's, hey, how does it look? And can I recognize something from it? Okay, purely qualitative, and I'll tell you what, probably the first indication for a lot of people is qualitative. Okay, if you know your system, qualitative is going to be your first indication. So that's certainly, in this situation, zoom in helps a little bit. That's not what we like our startups to look like. Okay, we don't like all that hunting. Now, where does that become real powerful? When I have a baseline to compare it to. Okay, so critical to get that baseline. All right, so qualitative is probably one of your first indications. Another qualitative would be this here. This is a pump, okay, a centrifugal pump. And we're looking at about a 400 amp signal with a fairly steady, current, okay? Again, if we look at qualitative versus this, which one do we like? That's not hard, is it? And it doesn't take an engineer to look at that and say, wow, why is it different from the last time? Okay, qualitative indications, okay? Let's bring the guys in that know the mechanics and let's say, hey, we've got something going on here. In this situation, it's very likely going to be, in fact, I think there's a picture of it, cavitation, okay? With the bell broken on this pump, it was creating a severe torque change as a result of cavitation, okay? Now, on our submarine, cavitation was a big deal, okay? Because if you cavitate it, the enemies heard you, right, underwater. Not quite as big a deal in this situation, but this affected productivity and production. In fact, this utility plant had to downsize the amount of electricity they could produce as a result of the variations that they were seeing. And megawatts are expensive. That's the way, it's all about the megawatts is what we hear from our utility friends. So again, a situation where a pump, this actually was sent to TAW and broken down, and it's odd. I would have thought there would have been, they said that actually the pump was still pretty healthy. Yet you can see the effect that it had on the current was unmistakable. Okay, they said that they found a lot of some like plastic within the pump as well. I kept thinking they'd find metal chunks living up in there, but they didn't find any of the bell housing at all. So we asked the natural question: well, did they just drop this when they brought it out of the water? Were we seeing something else? Where did the plastic? They couldn't even identify what was inside the pump. But either way, guess what? There was something wrong, wasn't there? Okay, so qualitative, again, don't dismiss it, and don't dismiss the guy who says, I don't know what's wrong, but it sure looks funny. Okay, a lot of times that means a lot more than you might think. Okay, I'm sure you get the same with ultrasound. Ultrasound's got to be a lot of the same. Okay, qualitative, what does it sound like? I heard it last month, and now it sounds very different. Did the load change? Did the system change? Again, qualitative, don't dismiss it. It's a big deal. All right. Now get towards the end, and I'm probably racing through this pretty fast, which is really, that's okay, because I'm sure there's 1,000 questions. But the process analysis part of this becomes a very intriguing element. In this situation, this is an automotive industry. Okay. Now in the automotive industry, there's a variety of processes that occur. Sometimes there's robotics involved, moving things from here to there, elevators that move engine components from here to there. Okay. In this situation, it's a fairly long process. Okay, and you can see that there's actual 6 major elements within this process. And a simple RMS envelope of your current signature can be very helpful in this situation, okay? So in this situation, if you look, when we went, and I think there's nope, that's not it. There's a little bit more activity, I thought, but in the article, we try to explain what some of these are, okay, in terms of how they affect it. But every one has its own characteristic, okay? Every function, every part of that process indicates something specific, whether it's lifting, whether it's moving, whether it's transferring. Some of you are maybe you're involved in robotics, okay, or there's a variety. Like the last time I remember a fairly intense one was it was robotics, and it involved a couple different drill. It was a drill actually on a I want to say it was a spindle, but there was at least 5 different directions that it had to drill in one process. Okay, by capturing that. Okay, and being able to overlay that, compare it to the last test, a variety of things can be brought out of that. Okay, so in this situation, it starts out at 1. You can see that the longest process is number 4 here, and this is about a 30-second situation. Okay, a 30-second process, not a long process, but certainly one that repeats itself probably multiple times in a day. So imagine the power if all of a sudden the fourth element of this increases to 15 seconds long. Something's wrong there, isn't it? It may be a little more subtle that the stage 3, doesn't have quite as much current. And if it doesn't have quite as much current, it may have just a little bit less torque. It may take a little bit longer. So all of a sudden they're complaining about the process or the end game of whatever's being pulled off this process. Say, hey, it's not the good quality we're expecting. Back to the process analysis. Now, where are we seeing all this? Through the electric motor. Okay. So remember, your electric motor can be your eyes, maybe your ears, okay, into the process itself. All right, and give you a lot more information about possibly what's going on with your load, with your process itself. Now, surprising even to me, that's it. It's a miracle, actually, that I was able to give a presentation. And how late was I up here? 25. Using my introduction takes 20. So I blame Adrian.
Yeah, that's my fault.
Adrian should have talked about me longer. No, I don't have much to talk about. Give me some questions. You guys got to have something. VFD motors. VFDs are magical. If you said in our support group, I'd say 50% of the conversations involve VFDs. And VFDs are a necessary, I don't want to say necessary evil, they have really changed the face of process and production, okay? Certainly when it comes to robotics, you're going to have variable frequency drives. And a lot of them are feedback circuits and stuff like that coming so that they know where they're located at, right? And nothing better than a VFD on that. We look at VFDs not from the transient, let's say the rise time transients. The transistors are firing in microseconds, right? We look more at the VFD and what it provides to the motor. So we like to test line side of the drive because the drive has quite an effect on the distribution. And we like to test load side of the drive, which actually is affecting the motor, right? So I think the biggest thing we've been able to come to a conclusion is that, is it the motor or the drive that's caused a nuisance trip? And it doesn't take too much, even from an RMS perspective. By RMS, I mean not looking at the microsecond transient rise time of an insulated gate bipolar transistor, but just, hey, what does the signal look like going to the motor? What is the frequency and how is that changing? So probably the biggest hurdle we have right now for VFDs is we have not optimized our system for speed assessment, right? So if you look at a lot of our demodulated captures, okay, they're not optimized for drives, and we need to rethink that a little bit. Okay, so as comfortable as we are at saying, hey, is it the motor or is it the drive? And that's pretty easy for us now. We could take it a step further. So a lot of the mechanical analysis that we talked about today is less effective in a variable frequency drive because of the fact that we're not sampling at a frequency optimized for a 43 hertz drive. Good question.
Could you infer the speed change from the length of the step? Like if you had a VFD responding to a set of instructions like the curve behind you, 4 could still get longer, couldn't it?
Right. The question is, can we infer a speed change? Now, by speed change, you're talking about the rotation of the motor itself?
Yeah, or speed of motion.
I would say yes, because a lot of times in the processes that we end up seeing this stuff on, they're not using rotations as much as they're using placement, right? So they're going to move it like, say, a motor-operated valve, okay? Right. So when we're looking at a motor-operated valve, what's interesting is the ones I looked at recently, they weren't nice and smooth. I always thought it'd be, hey, there's a certain amount of current required to lift that valve off its seat and transfer it over to the end, and then once it sits, once it seats, it triggers it again. That's not what I'm seeing a lot of times. What I'm seeing a lot of is pulsing motor-operated valves, right? It'd be very interesting to see, what you guys can hear through the ultrasonic side on that, actually. Because for us, we're seeing these pulses, and there's pulses, and it's pulses, and it's pulsing, and they're varying in width. But, for us, it's more, how long did it take? And that's about it. But for the ones that are not like that, they're not the pulsing, those are a lot more like what you see here, okay? And so what you can tell is, hey, it took 15 seconds to get that thing shut. And it was shut as a result of probably a position sensor. Although I think that the more critical you get, they're using torque. They want to know that, hey, we've hit a certain torque and it shuts it down. But if you're looking at that and you can see the current rise up as it seats and then it shuts down, that should be very consistent. And anything that creates, let's say if the time to seat took twice as long, they need to start looking at the seals. Something's going on with that. But that's just one example. So the question was good. It's not so much a speed reference, but probably a traveling reference. How far did that widget travel? And that's what we're going to be able to tell. Because they're going to keep sending the signal to it until it does what it's supposed to do. And if it's taken 30% longer, somebody needs to look up into the mechanical. Is there a resistance? Something's going on there. But again, we're using electrical current to look inside the application. Okay, and I'm challenging you, what can you do from the ultrasonic perspective through the motor to look into the system? It'd be an interesting challenge. Any other questions? I think there was one in the back. I already answered it. We're good at that kind of thing.
Anyone else for Noah? Okay, thank you, Noah.